Now we continue on with our study of set theory, and we are going to, in this next section, in the next few slides in this video, we're going to be using the set of natural numbers, which the set of natural numbers is the following. It's just the natural numbers are the numbers from 1 to infinity, the whole numbers, whole positive numbers from 1 to infinity. So this is the set of numbers we are going to be living in. The natural numbers do not include 0 or the negatives. So these are the numbers we're going to be living in as we solve the next few problems. For example, we have this slide here. Express the following using the list method. So list out the set A, which is the set of natural numbers less than 5. And feel free to take a minute and try this on your own. So we have the set A, we have our set notation, and we have the set A is the set of natural numbers less than 5. So if I'm counting down, 4 is less than 5, 3 is less than 5, 2 is less than 5, 1 is less than 5. We don't go below 1. We don't have 0 or negatives, so that's just our answer. Number 2, we need the set B is the set of natural numbers greater than or equal to 25. So this time we have the set B, which is equal to, and we have to be careful here. We have greater than or equal to 25. So we include 25. And now we can work our way up. 25, 26, 27, and it's going to go on forever. So I put ... comma, ... and I'll close my bracket. One thing that you'll realize from watching these videos is I'm very bad at drawing a curly bracket. And then in number 3, we have E is equal to X, given that, this little line means given that, X is in, this is an element of, X is an element of the natural numbers, and X is even. So, which of the natural numbers are even? Well, we have E is equal to all of the even natural numbers, which are 2, 4, 6, 8, onward to infinity. And so this is a little bit of natural number set notation. Continuing on, we have number 4, which simply says C is equal to all of the x values such that x is a natural number. So this is just all of the natural numbers. This is the way to write our natural numbers, which we write like this. We already have the answer. This is just the set notation way of writing it. And then we have number 5, D is equal to X, given that X is a natural number, and X is between 70 inclusive. This says that 70 is less than or equal to X, but X is less than, not inclusive, less than 100. So we have the numbers. D is equal to, we're starting at 70 and we're including 70 here. Remember your inequality symbols. 70, 71, and we're going to go all the way up to 100, not including 100. So we're only going to go up to, let's say, 95, 96, 97, 98. I should have started a little higher, 99. And so that is our set. I could have listed them all out, but it would have taken an extra minute. So that is our answer to that question. Now, elements. How many elements are there in the following sets? Well, we have 1, 2, 3, 4. We have 4 elements here. There are 4 pieces in this set. In number 2, there's one element here. Number 3, if you count them, we have 13, 14, 15, 16, 17, 18, 19, this is hard, 20, 21, 22, 23. We actually have 11 elements in number 3. If you were to write them out and mark them off, you would have 11 elements. And then we get to the question which is a little more challenging. This question says, how many elements are in the set containing the empty set? So this is a set containing the empty set. So do we have 1 element here or 0? And for what we care about, we actually do have an element here, and that element is the empty set. We're going to count it because it's represented. So we're going to say that this set has one element. Whereas, if you just had the empty set without the brackets, this would have 0 elements. Similarly, if you just had the brackets without anything inside, this would have 0 elements. So there are a few tricky things, a few weird things, but if you explicitly count the empty set, the general idea is that it is one of the elements in between these brackets. So there is one element between these brackets. Okay, so that is the number of elements. Now, the cardinality number of a set A is represented by a little n next to the A, is the number of distinct elements in the set A. The cardinality of a set is just the number of distinct elements. So what we just found is we found the cardinality of these 4 sets. So take a minute and write this definition, and then we will move on. So because of that, we have a few definitions which differ a little bit in surprising ways. Our first one is equivalent in set theory. The word equivalent in mathematics means set A is considered to be equivalent to set B if set A and set B contain the same number of elements. Or, written in our notation, A is equivalent to B. 3 equal signs, or three lines means equivalent. A is equivalent to B. If and only if, 2 F's mean if and only if, the cardinality of A is equal to the cardinality of B. So 2 sets are equivalent if and only if they have the same number of elements. For example, let's look at these couple examples. A here is equal to x, given that x is a natural number, and x is between 3 and 7 inclusive. So let's figure out the cardinality of A, the little n of A. The cardinality of A is going to be 3 is included, 4, 5, 6, 7. So if I put commas here, A is equal to 3, 4, 5, 6, 7. And how many elements are there? 1, 2, 3, 4, 5. The cardinality of A is equal to 5. Notice I don't care about those numbers. I don't care about the 3, 4, 5, 6, and 7. It could easily have started at 4 and been 4, 5, 6, 7, 8. Either way, the cardinality of A is still equal to 5. Now, B is equal to X, given that X is a vowel in the English alphabet. So let's find the vowels of the English alphabet. The vowels are A, E, I, O, and U. And sometimes Y, but we're going to ignore that for now. And we have 1, 2, 3, 4, 5 elements of this set. So the little n of B, the cardinality of B, is equal to 5. There are 5 elements in that set. 2 sets are equivalent if they have the same number of elements. Put those 2 things together, and we actually have that A here is equivalent to B. It's a weird notation thing. It's a wordy thing that you have to get used to. Equivalence, A is equivalent to B if they have the same cardinality, if they have the same number of elements. And we see that B has the same number of elements as A here. So A is in fact equivalent to B. Now don't worry, because we do have a definition for a word that's much easier to understand. We have another definition, equality. Set A is equal to set B if and only if set A contains the same exact elements as set B, regardless of order or permutation of elements, which means it doesn't matter which comes first, which comes second. If they have the same elements, then A is equal to B. Notice the 2 lines in the equal sign instead of equivalence. A is equal to B if and only if A and B contain the same elements. So let's look at. So what that means is if you have A and B, in this case, A is equivalent to B, but A is not exactly equal to B. A is not equal to B. Because here we have A, E, I, O, U, and up here we have 3, 4, 5, 6, 7. So equivalence and equality are 2 different things in set theory. Now moving on, another thing that we'll need is a finite set is a set with a beginning and an end, a set with a very specific numerical cardinality. For example, the set here, n of this set, the cardinality of this set is equal to 4. Whereas an infinite set is exactly what you'd expect it to be. This is the set of all multiples of 3. Well, they go on forever. Or I could say n of this set, maybe this is set 1 and this is set 2, n of set 2 is equal to infinity, has an infinite cardinality. I should write equivalent to infinity, equivalent to 4. Now we have another definition, a subset. We're almost there. A subset is, set A is a subset of set B, written as A is a subset of B. So this is a new symbol for us. We'll be using these symbols a lot over the next few weeks, so don't get overloaded with them. You'll see them often enough to memorize them. A is a subset of B if every element in set A is also an element of set B, which makes sense. The empty set is a subset of all sets. The empty set is always a subset of any set you have, which is similar to the idea that 1 is always a factor of any number. For example, even prime numbers, like the number 13, has 2 factors, 1 and itself. Any set has the empty set as a subset. So now let's do a little bit of practice with this. The symbols here are is a subset, and you guessed it, is not a subset to describe these sets. We have A is equal to 1, 3, 5, and 7. B is equal to 1, 3, 5, 7, 9, and 11. And we want to know if A is a subset of B. Well, you see, those are the same element, those are the same element, those are the same element, those are the same element. A is inside of B. All of the elements in A are represented in B. So A is a subset of B. A is most certainly a subset of B. Same thing here. We have A is equal to 1, 3, 6, 9, and 11. B is equal to 1, 3, 5, 7. Well, they both have a 1, they both have a 3, but they don't both have a 5. And they don't both have a 7, and they don't both have a 6, a 9, or an 11. So in this case, they are not, neither of them are subsets of the other one. So we have that this is not true. It is not a subset. Moving on. We have A is all of the letters in the word proof. B is all of the letters in the word roof. So we have A is equal to P, R, O, F, all of the letters in the word proof. B is equal to all of the letters in the word roof, R, O, F. And it's often a lot easier to see the answers to these if you write them in list notation. B is absolutely a subset of A. B is definitely a subset of A. R, O, and F are all represented in B, and they're all represented in A. Moving forward. A is all the letters in the word banana. B is all the letters in the word ban. So let's write A first. We have a B, we have an A, we have an N, and that's it. And then if we write B, we have a B, an A, an N, and there we go. And so are all of the elements of A found inside of B? Well, they are. So this is A is a subset of B, despite the fact that they're the same set, which is interesting. A is a subset of B. So this is actually, if you look at this symbol, it could, if you made a little point here, remind you of that symbol. Less than or equal to. The or equal to means the same thing here. A is a subset of B means A is either equal to B or something that B contains. Which leads us to yet another definition. A proper subset. Set A is a proper subset of set B, expressed as A is a proper subset of B if set A is a subset of set B and set A is not equal to set B. So proper subset, it doesn't have the equal sign. A cannot be equal to B. So now in this case, we have questions where we're asked, is it a subset or a proper subset? And we have A is equal to X, given that X is a person living in San Francisco. B is equal to Y, given that Y is a person living in California. Now, I can't list all the people in San Francisco and all the people living in California, but I can say anyone living in San Francisco is absolutely in California, living in California. So we have that it is a subset. But not only that, but there are plenty of other people who live in California. So we could go further and say A is in B. A is simply a proper subset of B. Because these sets are most certainly not equal. A is much less than B. Similarly here, A is equal to 2, 4, 6, and 8. B is equal to 2, 8, 4, and 6. This time, we have that they're definitely at least a subset, but are they a proper subset? They are not, because A is equal to B. A equals B. So we have to have the or equals to. We have to have the little equality symbol here. And now this one is just to see if you're paying attention. So take a minute and see if you can get this one. A is equal to the empty set. B is equal to 2, 4, 6, and 8. A is a subset of B. A is a subset. The empty set is a subset of all sets. So now let's look at subsets. In fact, let's take a break and do a few problems, and then the next video will be about subsets.